Welcome to our reading project. This is based on advanced game tree research called as Monte Carlo tree search. This is a short recap on the game trees that has been taught by Professor Mandal in our course structure. Game trees for two plays that we have considered here involves min and max nodes. Player 1 eyes for the best possible move, that is the maximum value child node, to play considering the worst position it may lead them to, that is the minimum value grandchild node. Each move is rated based on the heuristic estimates that has been considered while making a game tree. This forces the machine to trace all the nodes and backtrace it so that the minimum and maximum values can be placed upon the respective child nodes and the parent nodes. A simple common sense which reduces the number of nodes very to a small value. This is called as alpha beta pruning. When we consider the alpha as the lower bound of the maximum node and beta as the upper bound of the minimum node, in the simple condition where alpha is greater than beta for the parent-child combination, the nodes under this can be pruned based on the value that these set of nodes won't affect the above the whole holistic picture won't be affected by these set of nodes. There are limitations to alpha beta pruning. Full node space must be spent to find minimum maximum values and backtrack so that the values has been updated. It sets for the ideal move to play by considering all the options available for player 1. So this is good in cases where we have the full set of data available. When there is probabilistic values, it's very tough because it doesn't subject to, it's sometimes subject to assumptions. It stucks. This is called huge space complexity. It traces for ideal moves and expects the opponent to play the same. It's not the case in the realistic situations. Now, let's give an intro to the Monte Carlo tree search. For decades, alpha beta has been the standard for tree search in two-player games. The alpha beta algorithm requires a good evaluation function in order to satisfy tree search. However, no such evaluation function is available for a complex game. Alpha beta is basically a domain dependent. An alternative which emerged around that time was to use Monte Carlo simulations, which has been developed in the molecular structures and other molecular simulations. This alternative for positional evaluation function has been implemented in 1993 by Brugman. Soon it was developed into a complete Monte Carlo technique called Monte Carlo Tree Search MCTS in short form. It is the best first tree search guided by the results of the Monte Carlo simulations. It has been used in other board games like chess and shogi and the games that can be solved and artificial intelligence. Now, the basis of this MCTS stands on the mimicking of the human psychology. It doesn't do any rocket science. It simply sees what human brain does and just mix it into an algorithm. Human judgments on problems ranging from trivial simple intuitions that we don't even know that we are making decisions to complex decisions that we think for several months and years based on only two simple traits. Opinion and experience that we have gained from our childhood, that we have listened from books, that we have seen from others' experiences are stored in our brain, and these past events slash situations is accompanied with the implicit trust value, which means the situation that there are situations that will weight more, there are situations that will weight less, and both are there in our brain. And when depending on the problem statement, we choose whatever is needed. But it's a known truth that people have to explore ideas because you have to have some out of the box thinking. To have this out of the box mentality, we often explore new ideas, experiences, and we often search for new experiences, thus gaining knowledge, skills, updating the pre-existing opinions. As we all know, when we are child, we'll have some existing opinions that we have gained from intuitions, and that as we grow on in adolescence and adult age, we'll see new experiences, new opinions, and we'll update the pre-existing opinions. These two yet trivial yet powerful traits are implemented in Monte Carlo research. Trust networks. As we have said in the previous slide, there is an implicit trust value. We don't weigh every experience in a similar way. We weigh a similar experience more than the other experience. Similarly, we want to do that in an artificial intelligence. So we coined a term called trust network. This is derived from a neural network, which is quite normal in machine learning. A trust built upon the events as simulations, which are in the past and can be incomplete, as in the situations that we have seen as in when this is the basic analogy of the human brain. So the situation that we have seen in the normal lives won't be always complete. We judge situations, we judge people, we judge so what we get is not complete information. We have an incomplete information and we get a trust value of profit. Similarly, the three trust network does the same thing, equivalent to probability of winning from the child node. So the probability of winning from the child node is same as the trust network. What is the probability that you will win if you go into that child node is the trust value that you have on that child. This is expressed as an edge value between the parent respective child node combination. Computational power is directed based on the trust value. There are other simulations and other selection techniques that will play an important role, which will be explained by my friend later on. Now, as we have seen the trust, there are two major components. Both are usually interdependent. One is the trust network, aka opinion and experience. Other one is exploring new ideas. This exploitation and exploration. We have seen the exploitation part, and we are seeing the differences between both of them. Exploitation of nodes is done based on the trust value obtained from the trust network. As you have seen, trust value, it's an often case of the probability of winning when you come to the game trees. Exploration of nodes values are done in order to avoid oblivion. We don't want to miss anything. We just want to have a complete holistic view so that we are aware of the decisions that we make. This exploration balance, this is called as that we can't mean it's a age-old question whether it's exploration is important or exploration is important. But as we all know, both are very much important and we need to have a balance. This weightage to these are given based on simulations that are more number of simulations than on exploration, less number are done on explorations. Such that both are done.
So far, we've looked at what game trees are and what Monte Carlo tree search is and how it differs from alpha beta pruning. So now let's look at the key steps in Monte Carlo tree search, which are selection, simulation, backpropagation, and expansion. These steps depend on one another and happen as and when necessary. We'll expand upon this in the following slides. So let's look at the selection procedure. So this is the game tree that we have constructed, where each of these leaf nodes represents either a win for blue or a win for red. Alright, and in alpha beta pruning you would have had heuristic values at each of these nodes, but here you have probabilistic values. So let's look at what this value actually represents. This probability at each node represents the probability of red winning. You can take blue as well, but we have kept it uniform throughout the entire graph, keeping it the probability of red winning. So what 5x7 represents is we've played 7 games at this node, and out of those 7, red has won 5 times, right? So it's 5x7. So here out of 4 games played, 3 were won by red. So now how do you determine the value of the parent? So out of a total of 7 plus 4, 11 games played, 5 plus 3, 8 were won by red, right? So this is how you determine the probability of the parent, and we've constructed the whole graph in this way. So let's start playing from the top node. The first move is played by red, followed by blue, and so on. So as you can see, 83 games have been played at this node, that is the sum of all these, and 42 have been won by red. So if you're at this node, directly looking at the probabilities, you're more inclined to play this node more, right? Because you have a more chance of winning. And this node has an okay chance of winning, and this node has a poor chance of winning, right? So the exploitation part of Monte Carlo tree search will ask you to play more games with this node, and the exploration part will ask you to play a few games with this node as well. So let's actually look at how that selection process works. So here, this S value is determined for each and every one of the children, and the one with maximum S value is chosen to play with. So here, Vi is the probability of the child node. That is, in our case, it was 30 by 46, right? So that is what Vi is, plus root over C1 is some constant into log of n. N is the number of games you've played at the current node, which is 83, and that is divided by ni, which is the number of games you played at the child's node. In our case, it was 46. Plus, what this term represents is that in any game, there are a set of experts, right, in that game. So you give a weightage to the opinion of those experts as well. So Pi represents the probability of an expert to play that particular move. Alright, and that is divided by ni plus 1, which means as you play more and more games at a particular node, you give lesser weightage to the expert's opinion, right? Because you've gained enough knowledge to make your own decisions. That's what this means. So let's see how this actually translates in our example. So you're at the parent node. Let's look at the S value for the 30 by 46 wala child, which is our highest probability of winning, right? So Vi, this term is the exploitation term. 30 by 46 is the probability of red winning if you choose that thing, plus root over the constant we've chosen is 100, just for simplicity, into log of 86, which is the total number of games you've played at the parent, divided by 46, which is the number of games you've played at that child, right? Plus, and this is the expert's opinion term. 100 into expert is bound to play it 5 out of 8 times, divided by the 46 plus 1 times you've played at that child node, right? So for each level, you choose a child node with the maximum S value, and you play that. So as you can see, as the number of games you play at the current node increases, that is, suppose this is the number of games you played at the parent node, right? So the more games you play, this will increase in logarithmic time, whereas this increases in linear time, right? Because you're bound to play more games with this child because it has a more exploitation value. So this increases in logarithmic, whereas this increases in linear time, and overall this term's value decreases, right? So this is how Monte Carlo tree search maintains that balance between exploration and exploitation. So as the number of games increases, like I said, the numerator increases logarithmically and the denominator increases linearly, and overall that term reduces. So for a term with higher exploitation, the exploration thing decreases. So this is our the node with 30 by 46 probability. Assume you've played 200 games, right? So assume you've played 200 games at this node. So out of those 200, if you played all those 200 games with this particular node itself, let's look at what the selection value will be after 200 games, right? So the nodes we are considering here is this one and this one, since one has the highest and the other has the lowest probability. So for the node with which we played all the 200 games, the probability will translate into this. So you play all the 200 games with this node, so the exploitation value turns out to be this, plus, so give more importance to this term. Here, this ln of 86 is converted to ln of 286, but this 46 becomes 246, right? So you've played all 200 games with this same node itself. So this has increased logarithmically, whereas this has increased linearly. So this overall term has lesser value than what this had, right? But let's look at the selection value for the node with the least probability initially. So after playing 200 games, this value has increased, whereas the bottom value has not increased at all because you haven't played a single game with it. So in this thing, what you see is 1 by 8 has a higher selection value than any other node in that level. So The S value asks you to play this node first, this node right now, after 200 terms, right? So this is how Monte Carlo tree search maintains a balance between exploitation and exploitation. That is, even if you play 200 games with the same node, which represents the exploitation bit, you also play a few games with the node with the least probability, which is the exploration part.
The next step of Monte Carlo tree search is called simulation or playout. In simulation, we need to play random moves till we get a result, either it's win or loss or draw. This is the basis of Monte Carlo tree search. Here, in addition, we can also use pseudo-random moves like a heuristic function. For example, in chess, we should not be checkmated, or we should keep maximum number of pieces in the board. So, more simulation there are, and the bigger the stats tree and more accurate the node values. Back propagation. Whether it's a win or loss, we need to update the result to each node till the node where we expanded. In this step also, we need to update the number of visits at each node. Expansion. After selecting the right node, expanding used to increase the option further in the game, creating more child nodes. If a node does not give a decisive information, whether it's win or draw or loss, we need to expand the node. A threshold value is used to avoid unwanted expansions. Expansion results in out-of-the-box solutions where any general intuition won't guide us. For example, the child node x of t is assumed to be fully blue, that is, red's winning probability is 0. But on expanding it further, we get the real value, which is 2 out of 100. To explore these two winning ideas, we expand them. But to avoid unwanted expansion, we set a threshold value 100. Once the machine traced this node 100 times, it decided to expand them. Now, let's take an example using MCTS on tic-tac-toe game. Here is an expanded tree with approximate values for each child node. Note that we store two properties, the accumulated values and number of times we have rolled out. The information from the child node is back-propagated, increasing parent's node value and visit count. Now, we are calculating UCT score for selection of child node. It appears that the first node has the highest UCT score. We expand the first node even furthermore and create more child nodes to these nodes. Now these child nodes are again similar. Values are back propagated. We continue to run iteration of Monte Carlo tree search until we run out of time. The tree is gradually expanded and we explore the possible moves, identifying the best possible move to take. The bot actually makes a move in real game by picking the first child with more number of visits. For example, if the top of a tree looks like this, then the bot would choose the first action and proceed.